Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today's lecture is on bonding and chemical interactions, and we're going to cover 4 important objectives. The first objective deals with bonding. Here we're going to compare and contrast ionic and covalent compounds. We're going to explore the octet rule and its exceptions, and then we're going to learn how to distinguish between covalent and ionic compounds through a flowchart. The second objective will be focused on ionic bonds. We're going to explain why ionic bonds are commonly formed between metals and nonmetals. We're going to recall the major characteristics of ionic compounds, and then we're going to learn about lattice energy. This is going to be followed with a discussion on covalent bonds in the third objective, and here we're going to cover a lot. We're going to first learn the relationship between bond strength, bond length, and bond energy. Also, we're going to learn how to draw Lewis structures, and we're going to do plenty of examples. We're also going to discuss concepts like formal charges, resonance, geometry and polarity via Vesper theory, and atomic versus molecular orbitals. Last, we're going to discuss intermolecular forces. So we're going to specifically cover London dispersion forces, dipole-dipole interactions, and hydrogen bonds. We're also going to learn to order the intermolecular forces from strongest to weakest and predict what intermolecular forces are possible for a given interacting molecule. Now, to really motivate this chapter, it's important to note that almost every substance that we encounter consists of molecules or crystals containing atoms that are held together by chemical bonds. In fact, the only elements that occur in stable form as separate non-bonded atoms are the group 18 noble gases. So then this chapter is really going to be focused on introducing you to 2 important types of chemical bonds, ionic and covalent bonds. We're also going to learn that atoms and molecules, they can participate in weak electrostatic interactions. What are those? What are the different types of electrostatic interactions? And what does this mean is the focus of our last and final objective. With that, let's go ahead and get started on our first objective on bonding. When most elements come together, when most atoms of most elements come together, they can form molecules. And these molecules are held together by something called chemical bonds, which are formed when the valence electrons of the atoms interact with each other. Now, the interesting thing is that the properties of these new compounds are usually very different from the properties of individual atoms. So let's probe a little further. How do atoms join together to form compounds? For many molecules, the constituent atoms bond according to the octet rule. And the octet rule states that an atom tends to bond with other atoms so that it has 8 valence electrons in its outermost shell, thereby forming a stable electron configuration that's similar to that of the noble gases. Now, an example of an octet configuration is shown here for the noble gas argon. Notice how there are 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in its outermost shell. Now, the important thing to note here about the octet rule is that it is more of a rule of thumb because there's actually more elements that can be exceptions to the rule than there are that follow the rule. These exceptional elements include hydrogen, which can only have 2 valence electrons, achieving the configuration of helium. Lithium and beryllium, they bond to attain 2 and 4 valence electrons respectively. We also have boron, which bonds to attain 6 valence electrons, and also all elements in period 3 and greater, which can expand the valence shell to actually include more than 8 electrons by incorporating d orbitals. Then the question becomes, well, how do we keep track of these exceptions? And the answer to that is to follow a couple of rules. The first rule deals with incomplete octet. These elements are stable with fewer than 8 electrons in the valence shell. They include hydrogen, helium, and lithium, which are all stable with 2 electrons. It includes beryllium, which is stable with 4 valence electrons, and boron, which is stable with 6 valence electrons. And to build on that topic, we can also discuss molecules with electron-deficient atoms. When beryllium or boron is the central atom in a molecule, it will often have fewer than 8 electrons, and these compounds are considered to be electron deficient. The second rule deals with expanded octet. Any element in period 3 and greater, it can hold more than 8 electrons. Here's some examples. Phosphorus, it could hold up to 10, sulfur 12, chlorine 14, and there are many others. Now these elements, why can they do that? These elements have empty d orbitals in their valence shell, and that allows the atoms to accommodate more than 8 electrons. The last and final rule deals with odd number of electrons. Any molecule with an odd number of valence electrons cannot distribute those electrons to give 8 to each atom. So for example, nitric oxide, it has 11 valence electrons. So that makes sense that it cannot distribute those electrons to give each atom 8. Now, another way to remember the exceptions is actually to remember the common elements that almost always abide by the octet rule. They include carbon, nitrogen, oxygen, fluorine, sodium, and magnesium. And remember that nonmetals gain electrons and metals lose electrons to achieve their respective complete octets. With this information, we want to move into classifying chemical bonds into 2 distinct types, ionic and covalent. Now, ionic bonds are electrostatic attractions between oppositely charged particles. These bonds, which are usually seen between a metal atom and a non-metal atom, result from electron transfer. So in other words, in ionic bonding, 1 or more electrons from an atom with a low ionization energy, typically a metal, are transferred to an atom with a high electron affinity, typically a nonmetal. In addition, in an ionic compound, oppositely charged ions are held together in an ordered 3-dimensional structure called a crystal lattice. We're going to elaborate on that in the second objective. Now, in covalent bonding, an electron pair is shared between 2 atoms, typically nonmetals, that have relatively similar values of electronegativity. And the degree to which the pair of electrons is shared equally or unequally between the 2 atoms determines the degree of polarity in the covalent bond. So, for example, if the electron pair is shared equally, the covalent bond is nonpolar. And if the electron pair is shared unequally, the bond is polar. Now, the question you should ask next is, well, what variable do we use to determine what kind of bonding is occurring? And the answer to that question is electronegativity. Electronegativity, this is the measure of the ability of an atom to attract electrons. Each atom has an electronegativity value, and when 2 atoms are forming a bond, the difference between their electronegative values determines their bonding. With that, let's go ahead and work through this flowchart. We have 2 categories for bonding, covalent and ionic. Let's start with covalent. A covalent bond results when 2 atoms share a pair of electrons. Now, if the electron pair is shared equally, the covalent bond is nonpolar. Now, the criteria for nonpolar covalent bonds based off of the difference in electronegativity is any difference in electronegativity below 0.5. This constitutes a nonpolar covalent bond. Some examples are carbon bonded to hydrogen and carbon bonded to carbon. And actually, any atom bonded to a similar atom, so carbon with carbon or oxygen with oxygen, the electronegativity difference between those 2 atoms is going to be 0. So those kinds of bonds are nonpolar covalent bonds. Now, on the other hand, if the electron pair is shared unequally, then that bond is polar. And the criteria here is an electronegativity difference between the two atoms that are forming a bond that's somewhere between 0.5 and 1.7. So examples can include carbon bonded to oxygen or carbon bonded to fluorine. So if we go back up here on our table, carbon has an electronegativity value of 2.6, fluorine is 4. If we do the difference between those two, 4 minus 2.6, we get 1.4. And this falls between our range of 0.5 and 1.7. Therefore, the bond between carbon and fluorine is a polar covalent bond. What about now for ionic compounds, all right? In ionic bonding, valence electron from one atom is lost to the more electronegative atom, and this results in oppositely charged ions. The criteria is an electronegativity difference greater than 1.7. A good example is table salt, sodium chloride. If we go back to our table, sodium has an electronegativity value of 1, chlorine of 3.2. So 3.2 minus 1 gives us a difference of 2.2. This is greater than 1.7. Therefore, the bond between these two atoms is an ionic bond. Now, both ionic and covalent bonds are their own objective in this chapter, which will allow us to actually go into more detail. So moving into objective 2, we're going to focus on ionic bonding. Like we mentioned earlier, ionic bonds form between atoms that have significantly different electronegativities. The atom that loses the electron becomes a cation, and the atom that gains electrons becomes an anion. So as a friendly reminder, cations are going to have more protons than electrons. They've lost an electron and they become positively charged. On the other hand, anions, they have more electrons than protons. They've gained an electron to become negatively charged. The ionic bond now is the result of an electrostatic force of attraction between the opposite charges of these ions. Remember that electrons, they're not shared in an ionic bond. And for this electron transfer to occur between two atoms that are participating in an ionic bond, the difference in electronegativity must be greater than 1.7. Now, you are usually not expected to memorize electronegativity values, but recognize that ionic bonds are generally formed between a metal and a nonmetal. And also remember your trends. Electronegativity increases going from left to right on the periodic table and going from bottom to top. In addition, metals lose electrons to become cations, and nonmetals gain electrons to become anions. So for example, alkali and alkaline earth metals, so group 1 and 2 respectively, they readily form ionic bonds with the halogens in group 17. The atoms of those active metals, they loosely hold on to their electrons, whereas the halogens are more likely to gain an electron to complete their valence shell. The differences in bonding behavior for these classes of elements and their difference in electronegativity values explains the formation of ionic compounds. Now, earlier we mentioned the term crystal lattice. Let us revisit this now. Those oppositely charged ions, they're held together in an ionic crystal by electrostatic forces, and these forces are non-directional, so each ion is surrounded by several other ions of opposite charge, and they naturally adopt an arrangement that allows them to maximize attractions and minimize repulsions, and this results in an ordered three-dimensional arrangement of ions. Here what we see is the crystal lattice for sodium chloride. Each sodium cation in a crystal of sodium chloride is surrounded by 6 chloride anions, and each chloride anion is surrounded by 6 sodium cations. Now, the electrostatic attractions holding the ions together in a crystal lattice, they are strong. And because of the strength of the electrostatic force between the ionic constituents of the compound, ionic compounds have very high melting and very high boiling points. Now, the next thing that's important to cover in the realm of ionic compounds is now the measure of strength of ionic bonds. One way to describe the strength of an ionic bond is with lattice energy. Lattice energy is the energy required to separate 1 mole of a solid ionic crystal into gas phase ions far removed from each other. And we can predict the relative magnitudes of lattice energy by focusing on the attraction between two oppositely charged ions. This is where Coulomb's law comes into play. It describes the electrostatic force of attraction or repulsion between two charged particles as follows. It is K, this is a proportionality constant, multiplied by Q1, Q2, where Q1 and Q2 represent the charges of the two particles, all over R squared, where R is the distance between the centers of the two particles. Now, Coulomb's law implies that the lattice energy of a crystal increases with increasing ionic charge and decreasing ionic radii. And the lattice energy of an ionic compound is therefore influenced by both the charge and the size of ions. Charge, however, has a greater impact than size. To make sense of this, let's go ahead and tackle a couple of problems together. The first example problem says, place the following compounds in order of decreasing lattice energy. To do this, we're going to have to understand and apply Coulomb's law. We're not going to actually be doing any calculations as long as we understand how to use Coulomb's law to our advantage to solve this problem. So let's go ahead and write Coulomb's law. The force of attraction or repulsion is equal to the proportionality constant multiplied by Q1, Q2, over R squared. Now the numerator here, Q1 multiplied by Q2, this deals with ionic charges, and the denominator R squared deals with ionic size. And this lets us focus on two important ideas from Coulomb's law. The first is the higher the ionic charge, the stronger the force of attraction. And that's because Q1 and Q2 represent the charges of the ions, and both of those terms are located in the numerator. So the higher the ionic charge, the stronger the force of attraction. Now, the second important idea is that the larger the ions, the weaker the force of attraction. Remember that R represents the distance separating the two ion centers. Therefore, as ions get larger, R squared gets larger, and the denominator in Coulomb's law gets larger. If the denominator gets larger, then we have a weaker force of attraction because these two are inversely related. So, larger the ion, the weaker the force. Now, keeping those in mind, to predict lattice energy, we should focus on the charges and the sizes of the ions. But like we said earlier, charge is almost always more important than size. So we're going to begin by comparing the charges of the ions involved in this problem. So what we have is lithium chloride, lithium with a +1 charge, chloride with a -1 charge. We have sodium chloride, sodium with a +1 charge, chloride with a -1 charge, and then magnesium bromide, magnesium with a +2 charge, bromide with a -1 charge. Since the charge of the magnesium cation is +2, and everything else has a charge of magnitude 1, we can predict that the lattice energy of magnesium bromide is the highest of the three ionic compounds. So magnesium bromide is going to have the highest lattice energy. Now we're stuck between lithium chloride and sodium chloride and trying to determine which one of these now has a higher lattice energy and which one has a lower lattice energy. To compare the two, we need to consider the size of the ions. Both of them have the same anion, chloride, so we can really just focus on the cation, lithium versus sodium. Sodium is larger than lithium. And if it's larger, then R squared is going to be larger, the denominator is going to be larger, and F is going to be weaker. And thereby, lithium chloride is going to have the second highest lattice energy, and sodium chloride is going to have the lowest lattice energy. And so as we write our compounds in order of decreasing lattice energy, we have magnesium bromide with the highest lattice energy, followed by lithium chloride, followed by sodium chloride. And with that, we have solved our first example problem. Let's go ahead and move into the second example. This one says, based upon a consideration of lattice energies, which compound is expected to have the higher melting point, sodium chloride or sodium bromide? Now, the thing to remember here as we solve this problem is what we're really trying to figure out is, does sodium chloride or sodium bromide have a higher lattice energy? Because having a higher lattice energy generally means that you have a higher melting point. And so we're going to use Coulomb's law to predict which ionic compound has the greater lattice energy. We always consider two things here: ionic charge and ionic size. We're going to start with ionic charge. Since charge has a greater impact on lattice energy than size, you should always begin by considering ionic charge. Now we have sodium chloride and sodium bromide. Sodium chloride has a +1 charge associated with the sodium cation, -1 charge associated with the chloride anion. For sodium bromide, we have a +1 charge associated with the sodium cation, -1 charge for the bromide anion. Since both cations have a +1 charge and both anions have a -1 charge, ionic charge does not play a role in determining the relative lattice energies for these two compounds. And so we have to move into considering ionic size. Both ions have the same cation. Both of these compounds have the same cation, sodium. So what we really need to compare is the sizes of the anions. Chloride versus bromide. Bromide is larger than chloride, and that's because bromine is below chlorine on the periodic table, and the atomic and ionic radii increase as you go down the periodic table. Therefore, sodium chloride is going to have the higher lattice energy in comparison to sodium bromide, and that means that sodium chloride is going to have a higher melting point. And that is how we answer this example. With that, we can now go ahead and move into objective 3, which is all about covalent bonds. When two or more atoms with similar electronegativities interact, the energy that's required to form ions through the complete transfer of one or more electrons is greater than the energy that would be released upon the formation of an ionic bond. That is, when two atoms of similar tendency to attract electrons form a compound, it is energetically unfavorable to create ions. Rather than transferring electrons to form octets, the atoms share electrons, and this is covalent bonding. Now, when an atom wants to fill its valence shell, it can form a bond with another atom. Sometimes one bond isn't enough, so the atom forms multiple bonds. When two atoms just share one pair of electrons, this is called a single covalent bond. When they share two pairs of electrons, this is called a double bond. And when they share 3 pairs of electrons, this is called a triple bond. The more electrons they share, the stronger the bond. Now, one quick note here I want to mention is bond order. The bond order represents the number of pairs of electrons that are shared by two atoms. A single bond in which one pair of electrons is shared has a bond order of 1. A double bond consisting of 2 bonding pairs of electrons has a bond order of 2, and a triple bond, which has 3 electron pairs being shared, has a bond order of 3. Now, in addition to that, there are three things that describe a covalent bond: bond length, bond energy, and polarity. The bond length, this is the distance between the two atomic nuclei. The bond energy is the energy required to break the bond, and polarity refers to the distribution of electrons between the two atoms in the bond. So that's a one-sentence definition for each of these concepts, but we want to go into a little more detail. So let's start with bond length. This is the average distance between the two nuclei of atoms in a bond. As the number of shared electron pairs increases, the two atoms are pulled closer together, resulting in a decrease in bond length. And so for a given pair of atoms, a triple bond is shorter than a double bond, which is shorter than a single bond. Now for bond energy, this is the energy required to break a bond by separating its components into their isolated gaseous atomic states. The greater the number of pairs of electrons shared between the atomic nuclei, the more energy that is required to break the bonds holding the atoms together. And so, triple bonds have the greatest bond energy, and single bonds have the lowest bond energy. Now, this kind of information is summarized in this table here. All right, single bonds have the longest bond length and the weakest bond strength. Double bonds have a medium bond length, medium bond strength, relatively speaking, and triple bonds are the shortest bonds and the strongest bonds. The next thing we want to talk about is polarity. Polarity occurs when two atoms have a relative difference in electronegativity. When these atoms come together in covalent bonds, they have to negotiate the degree to which the electron pairs will be shared. The atom with the higher electronegativity gets the larger share of the electron density. And a polar bond, like this, creates a dipole where the positive end of the dipole is at the less electronegative atom, and the negative end of that dipole is at the more electronegative atom. So for example, if we take hydrochloric acid, HCl, chlorine is more electronegative, and it's going to pull the electrons a little bit more towards it. What this results in is a partial negative charge on the chlorine atom and a partial positive charge on the hydrogen atom. Again, a molecule that has a separation of positive and negative charges is called a polar molecule. Now, the dipole moment of the polar bond or polar molecule, this is a vector quantity that's given by this equation, Q, P equals QD, where P is the dipole moment, Q is the magnitude, and D is the displacement vector separating the two partial charges. Now, the dipole moment vector is represented by an arrow pointing from the positive to the negative charge like we drew over here. Now, this can also extend into multi-atom compounds, right? More than just two atoms with one bond, to more complicated systems, like for example, NO3. You can figure out the polarity of each individual bond, but you can also figure out the polarity of the molecule as a whole. And that contains a lot of important information that has consequences in a lot of fields, spectroscopy being one. We're going to discuss that a little bit in a few minutes in a later objective. But now, the next thing that we want to move into is discussing coordinate covalent bonds and covalent bond notations. A coordinate covalent bond is a covalent bond in which one of the atoms contributes both bonding electrons. And this occurs when one atom donates a lone pair of electrons to be shared with another atom that needs two electrons to form a covalent bond. Let's discuss this further. In a coordinate covalent bond, both of those shared electrons originated on the same atom. And generally, this means that a lone pair of one atom attacked another atom with an unhybridized p orbital to form a bond. Once such a bond forms, however, it is indistinguishable from any other covalent bond. And this distinction is only helpful really for keeping track of the valence electrons and the formal charges. These coordinate covalent bonds are typically found in Lewis acid-base reactions, so we're going to talk about them a lot more in our acid-base chapter. Now, what about covalent bond notation? Covalent bonding involves the sharing of electron pairs between atoms. The electrons that participate in these bonds are called bonding electrons, while those that do not participate are referred to as non-bonding electrons or lone pairs. To systematically track these electrons, scientists use Lewis structures, which are visual representation of the arrangement of valence electrons around atoms in a molecule. A Lewis structure, also known as a Lewis dot diagram, it represents the chemical symbol of an element surrounded by dots, each representing one of the s or p valence electrons. In these structures, bonding electrons are depicted as lines between atoms, indicating shared pairs, while lone pairs are shown as pairs of dots on individual atoms. Now, the number of dots around an element corresponds to the number of valence electrons, and that can actually be determined from the element's group number in the periodic table when we exclude transition metals. So this would be group 1, this would be group 2, and then we skip the transition metals. This would be group 3, 4, 5, 6, 7, and 8. And these numbers tell us how many valence electrons the atoms in that group are going to have. So 1 valence electron here for group 1, 2 valence electrons for group 2. Here is where we start 3 when we're ignoring the transition metals. So these elements in this group have 3 valence electrons. These have 4, these have 5, so on and so forth. Now, it's important to note that the number of valence electrons attributed to an atom in a Lewis structure may differ from the neutral atom due to bonding interactions. This difference results in a formal charge, which helps in understanding the electron distribution within the molecule. The formal charge of an atom, it can be calculated using this formula, and we're going to review this formula later, again, through some practice problems. But the formula is that the formal charge is equal to the number of valence electrons in a free atom minus the number of lone pairs of electrons, all right, the number of lone pair electrons, minus 1/2 the number of bonding electrons. And this gives you the formal charge. Now, we're going to take this information and we're going to learn how to draw Lewis structures, but that's going to be in the second part of this chapter. So we're going to end the video here. Please let me know if you have any questions, comments, concerns down below. Other than that, I'll see you in the next part. Good luck, happy studying, and have a beautiful, beautiful day.